to post this recording to my YouTube channel. All right, Chemistry 3102. So you have a combined spectroscopy worksheet that you're going to have to complete and hand in or submit towards the end of the semester. But we wanted to take a look at some practice problems today to sort of get in the hang of solving problems wherein we're going to be looking at not only an infrared spectrum, but also a mass spectrum, carbon-13, and also a proton NMR. And you can use the tables for the proton chemical shifts and carbon-13 chemical shifts and the infrared absorption frequencies from the David Klein book if you're currently enrolled in Chemistry 3101. But I do want to turn your attention to the tables that are in our textbook, in the Schafzahl book. So in your lab textbook, you have the IR table on page 116, and you'll find that this table is a little more exhaustive than the table in the Klein textbook. It's table 2M-1. The proton NMR shifts, you'll find those on page 129, and that is table 2N-1. And the carbon-13 NMR chemical shifts, you'll find those on page 144. Oops, 144, and it's table 2N-3. So I would recommend that you follow these tables for looking at the infrared and the proton spectra. All right, well, let's get started. So here's problem number one. It says, determine the structure. So we need to elucidate the structure of the molecule and annotate the spectrum. Well, you see that we have a beautiful IR. It looks pretty simple. There's not a whole lot on there in terms of absorbances. We have a mass spectrum. We're also given a molecular formula. We're given a carbon-13. We're also given a depth spectrum. And you might remember that in a depth spectrum, any signals that are pointing down are methylenes. Anything that's pointing up can be either a methyl or a methine carbon. So we have a depth and a proton decoupled. And then we have a beautiful proton NMR spectrum at the bottom. Now, since this is the first problem, hopefully you can tell that it's not the most complicated problem that you'll ever face in organic chemistry. You see that in the carbon, we only have one signal, right? And in the proton, we only have one signal. So let's get started. And the place that I like to start is by looking at the molecular formula. If the molecular formula is given to me, I always like to start there. And I use the formula for my HDI or my HDI or my U, whatever you want to call it, the hydrogen deficiency index or the units of unsaturation. And we'll say that our HDI is equal to 1/2 2 times the number of carbons plus 2 plus the number of nitrogens, subtract the number of hydrogens, subtract the number of halogens, like that. So if you take this formula, C5H10, you don't even need to use this formula, do you? Because you know that a saturated hydrocarbon has a generic formula of CnH2n plus 2. And here we have a generic formula, which is CnH2n, right? 2 times 5 gives you 10. And so we have an HDI here that is equal to 1. That means we have 1 unit of unsaturation. I have a question for my students who are online currently. If I have 1 unit of unsaturation, could anybody tell me what that would indicate? If I have an HDI that's equal to 1. And it's not a trick question. I don't like trick questions.
A ring of something?
Yeah, it could be a ring. Yeah, 1 unit of unsaturation could be a ring. Is there another option? Yeah, Advita says it could be a double bond. And you're both absolutely correct, right? This could either mean a double bond. So we could either have an alkene, right, a double bond, or a ring. Okay, so double bond or a ring. Now, my inclination, just based on the fact that we only have 1 signal in the carbon and 1 signal in the proton, I mean, the fact that we only have 1 signal in the proton and every carbon is a methylene, right? The only type of carbon we have in this molecule is a methylene. That suggests to me that since we only have methylenes in the molecule and they all must be equivalent because we only get 1 signal in the carbon, that tells me that we probably have a ring or there's some kind of symmetry in this molecule. Exactly. Okay, but before we get too far ahead, I want to talk about the IR and I also want to talk about the MS. I have a question for my students about the MS. You see that the molecular ion is 70, has a mass overcharge of 70. Could anybody tell me if there's a conclusion I could draw from this just by looking at my molecular ion, just the fact that it weighs 70, has a mass of 70? What kind of conclusion could I just draw from that? Boom, very quickly. What if I tell you that 70 is an even number, right? 70 can be divided by 2 to give you 35. If I have an even mass, what does that tell me? Does anybody remember the rule called the nitrogen rule? If I have an even mass, what that tells me is that either I have no nitrogen present, okay, so I'll say no nitrogen present, or I have an even number or an even number of nitrogens, right? Now, since my molecular formula here, you're like, Mr. Dion, what's your point? It says here that it's C5H10. There's no nitrogens in it anyway. I knew that from the beginning. Well, in order to annotate a spectrum properly, you should always indicate this. Even when you're given a molecular formula, if you're thinking, well, that's redundant, you know, it's already told, they already told me here there's no nitrogens, we still always indicate that. Okay, it's a very good habit to get into to indicate the number of nitrogens. Another thing I noticed about the mass spec is that there aren't a lot of fragments, right? There's doesn't seem to be many fragments produced in the infrared, or sorry, in the mass spectrum. All right, I was thinking about the mass spectrum. So if we look at the mass spectrum, I mean, right away you can see we don't have an alcohol, we don't have a carboxylic acid, we don't have a primary amine, we don't have a secondary amine, we don't have an aldehyde, we don't have a carbonyl, we don't have an aromatic ring. In fact, we don't have much in here at all, do we? The only thing that we really have here are sp3 hybridized carbon-hydrogen bonds just below the 3000 range. That's the strongest absorbance in this spectrum. And so hopefully you're starting to connect the dots here. I've only got sp3 hybridized carbons. They're all methylenes. I have no nitrogens, okay? And in my proton NMR spectrum, I only have one signal, right? Could anybody propose a structure for this molecule or just name what they think the molecule might be? Even if you are unsure, and you should know the name of the possible structure. Hold on, I can't see what my student wrote. Give me a second. Yes, thanks, Skylar. Stephanie, absolutely. You're both 100% correct, right? It's cyclopentane must be the structure. If you're not sure, let's take a look. Let's draw the structure of cyclopentane. It's a 5-membered ring. Okay, you can see that we have multiple axes of reflectional symmetry here and rotational symmetry. Each one of the methylenes in here, they're all chemically equivalent. So that explains why we only have one signal in our carbon-13 NMR spectrum. You see that every carbon is a CH2. They're all methylene carbons. And then in our proton, the same rationale applies, right? Every hydrogen is part of a CH2 or a methylene. There's going to be no splitting because they're all chemically equivalent. Remember, protons that are chemically equivalent do not split each other. And so there you go. We solved the problem. Now, in order for us to finish the problem out, we have to annotate the spectrum properly. Let me show you how to annotate the spectrum. Okay, you always start on the right-hand side and you go towards the left-hand side. Okay, every peak that you run into, you give it a letter of the alphabet, starting with the letter A. Now this one's pretty simple because we only have one signal, so we put A there. Then we put the letter next to the carbon it represents. Well, there's only one type of carbon in the molecule, so we can put it like this. You don't have to put A. You don't have to do that because I know that they're all chemically equivalent. And there you go. That's our A carbon. And now we've annotated the carbon spectrum. The same thing applies to the proton NMR spectrum. We write A next to our singlet here, that's around 1.5 parts per million. We have our one signal, and we know that it represents these two methylene protons like this, you can put a little A by them like this, and this tells me that those are my A protons. And I know that all the other protons are chemical equivalent. And there you go. Now you've annotated a spectrum. Give me a thumbs up if you think you can solve this one. If you're like, you know what, give me, 2-3 weeks alone, textbook, calculator, mainframe. I think you could solve this one. Are my students feeling somewhat confident about this one? Yes? Okay, good. Thanks, Skylar. Okay. Well, obviously, we're going to get into problems that are a little more complex than this. Before we do, I just want to mention, I probably have a lot of things that I want to mention, but something that just popped into my brain is that when you're proposing a structure, make sure you propose something that's reasonable. Okay? Don't be drawing structures that, you have 4 bonds to an oxygen and hydrogens with 2 bonds and Texas carbons with 5 bonds and this kind of stuff. And you might be laughing at me and saying, oh, I would never, or, who would do that? Well, I've seen everything. Sometimes we see students that propose things, their heart's in the right place, but they'll propose structures that can't exist. So make sure that your molecule could exist before you start proposing it. Okay, now if you go into the combined spectroscopy module in the Chemistry 3102 page on Canvas, you'll see that I've posted a document there that says it's called Strategies for Solving Combined Spectroscopy Problems. Now, in that document, I have sort of a 1 through 7 steps or 7 or 8 steps, I can't remember, wherein I kind of give you just a step-by-step method of let's do this first, do that first, do this first, do that first. But you know what? When I see a spectroscopy problem, I'm kind of like a kid in a candy store. I'm just like any other human. I can't help myself, right? What do I go for? The low-hanging fruit, right? If there's something that sticks out to you right away, there's no harm in just saying, okay, I'm going to zoom in on this right away. That's the first thing I noticed when I flipped the page over to problem number 2, right? I said, well, I have an absorbance at 1718 in my infrared spectrum. That tells me that I probably have a carbonyl, right? I have that strong dipole in that carbonyl, which produces a strong absorbance. There we go. So that's, something that I saw right away. It's just like, bang, let's go for that I might have a ketone. I know it's not an aldehyde because I don't see the aldehydic CH stretching at 2850 and 2750. But let's move on to our infrared spectrum. Maybe I should use a different color here. We have a beautiful carbonyl there. Let's move on. Let's see what we can find in the mass spectrum. I haven't even looked at the molecular formula yet, have I? All right. Well, the molecular formula, we have a fragment the molecular ion rather at 42. 72. Mr. Dion needs a new prescription. That tells us there is no nitrogen or an even number of nitrogen. Again, I know that you looked at the molecular formula and you said, hey, there's no nitrogen in there anyway. But like I told you, we expect you to always write this down, even if it seems redundant. Let's go ahead and calculate the HDI. The HDI for C4H8O is 1. So my HDI is equal to 1. Now it's starting to come together because I've got an HDI of 1 and I've got a carbonyl in my molecule. So that takes care of my double bond. Now, since there's only 4 carbons in the molecule and there's a carbonyl and it's not an aldehyde, I know that this is some kind of ketone. I mean, there's not many ways that I can organize 4 carbons and have a carbonyl in there and have a ketone. Okay, there's very few ways that I can do that. All right, so that's just to kind of get you thinking about, hey, maybe there's a way I could put this together. And I'm sure that some students have already started to piece this together. But let me show you the carbon spectrum. Let's move down here. You see that we have 2 types of carbon spectra here. Now, the proton coupled spectra, if you remember, if you're in my lecture class, 3101, I mentioned the proton coupled spectra in that class. However, I said we don't really deal with those a lot in Organic Chemistry 1 because sometimes the splitting, there can be a lot of overlapping and it can be difficult to see what's going on. Now, the reason why the person who came up with this problem produced or provided a proton coupled carbon-13 spectrum is because you can tell what's going on. And so you can see here that we have what looks like, this looks like a quartet, 4 peaks. You can see this looks like a quartet, and then this looks like a triplet here. Well, let me tell you what those mean. It's the same thing as kind of like the N+1 rule. In that when we have a methyl group, if you have a methyl group, you'll get a quartet, okay? If you have a methylene, you're going to get a triplet. If you have a methyne, you get a doublet, okay? And if you have a quaternary carbon, you end up with a singlet. All right, so what does that tell us? That tells me that right here, I have a methyl group. Here I have another methyl group, and here I have a methylene, right? And if you're wondering, where are you getting that from? Look, if this is a quartet, right, that represents a methyl group. Here I have another quartet that represents another methyl group, and then this triplet represents a methylene. Now all of my carbons are accounted for, aren't they? Because I've got my carbonyl carbon, a methylene, and two methyls. They have different chemical shifts, so they're in different electronic environments. All right, let's go back to our carbon spectrum. So how do we label the signals? We start on the right-hand side, A. The next one is B. The next one is C. And the next one is D. Everybody in the class should have it labeled the exact same way. If we skip ahead right down to the proton, you see we have a triplet here. We have a singlet here. And we have a quartet here. So we would label these A, B, and C, right? Same thing every time. Okay, let's go back to our carbon. We have the methyl, another methyl, and a methylene, and we also have this carbon up here, which is a singlet. That tells me that this carbon is not attached to any hydrogen, so it must be my carbonyl carbon. But that makes sense because I know that the chemical shift of a carbonyl carbon is usually going to be in the 150 to 200 part per million range. You could probably solve this problem already without looking at the proton, but let's go ahead and look at it. You can see that we have a triplet and a quartet. It's hard to tell, but it looks to me like their coupling constants are the same. And whenever I see a triplet and a quartet, that makes me think that I might have an ethyl group. Over here, I have a singlet. And you can see that the integration here for this singlet, which is signal B, is the same height as A. And then I have this other one over here for C. Now, I've gone ahead and measured these already, and you can take a ruler and do that. And the relative heights here are 3, 2, and 3. So that tells me that this signal must represent a methyl group. This one must represent a methyl group, and this one here must represent my methylene. Okay, we've probably waited long enough, and you're like, I'm sure that some of you are like, Mr. Dion, you're going too slow. Could anybody elucidate the structure of this molecule? I know that we haven't looked at ketone nomenclature, but could anybody describe the molecule even if you have to unmute your mic? I don't care what you call it because we haven't studied ketone nomenclature. But could anybody tell me what this might look like? Or just even describe it? Okay. Well, the only way that I can think of to put these atoms together in my carbon is if I have a methyl and a methylene like this, to have a carbonyl, and then to have another methyl group like this. That's the only way. Yeah, Advita, it's called 2-butanone is the name of the molecule. Absolutely. Okay, 2-butanone. Again, we haven't covered ketone nomenclature, so don't stress about that. But 2-butanone, I think, is partially responsible for the flavoring in microwave popcorn. All right. Where was I? So we have A for our methyl group. So we have the two methyl groups, right? A and B are the two methyl groups. So which one is it, right? I can put A here, B here, A here, B here, but I should be able to differentiate between those two, shouldn't I? Right? Which one of those is going to be the more deshielded methyl group? It's going to be the one that's closer to the carbonyl. So this must be my B methyl group. This would be my A methyl group. My carbonyl is carbon D, and then my methylene is going to be C right here. If we take a look at the proton NMR spectrum, we'll draw the compound out like this. The proton's probably a little bit simpler to label. We have the A protons that are the triplet. That must be these protons here because they're coupled next to the two protons. 2 plus 1 gives me 3, N plus 1 rule. I have my B protons, which are 3 protons that would give me a singlet, which are good. And my quartet, which is C, which again is the methylene protons that are coupled next to the methyl. 3 plus 1 is 4, which gives me the quartet. If we go back to the MS, there is a fragment in here that I identified with you when we covered mass spec earlier on in this class. I talked about fragments that could weigh or have a mass overcharge of 43. For example, a propyl cation or an isopropyl cation has a mass overcharge of 43. But I also told you that an acyl cation, so I'll just draw it like this. Okay, the acyl cation like this also has a mass overcharge of 43. So that's a result of fragmentation here. Anyhow, so this is this fragment right there. I'm not so concerned with you labeling fragments in the mass spec. If you really want to, you can do that. But most of the structures should be able to be solved without labeling fragments or identifying fragments. Okay, and you don't have to draw out the mechanism of the alpha fragmentation or anything like that. If you want to, be my guest, but it's not necessary. Somebody asked a question about the mass spec for the molecular ion. What's NO? Molecular ion, N plus 2. I mean, you can say here the same thing. I mean, you could say that since there's no N plus 2 peak, so we have no chlorine and no bromine present. That works too if you want to include that. You'd say there's no chlorine or bromine present in the molecule because we have no N plus 2 ion. Yeah, that works. No problem. All right. There we go. Give me a thumbs up if you think you can solve that one. Stop me if you have a question. Is everybody following me on that one? 2-butanone. So we've got cyclopentane and 2-butanone. Remember, we need to propose structures that make some sense, seem reasonable. Thanks, Skylar. Good. All right. Problem number 3. I'm going to give you a couple seconds to take a look at this one. Hopefully you have it printed out, but you can see that it's pretty simple. I only have one signal in my proton, right? So if you just want to do this, A. In my carbon, I have 2 signals. I have A and I have B. So there's 2 types of carbons, 1 type of proton. What else? I don't have a whole heck of a lot up here in my IR, do I? It's kind of like a wasteland up there. But I do have a strong absorbance here around 1700 roughly. So this is probably a carbonyl. And if I look at my molecular formula, C8 or C6H8O2, my HDI or my U is equal to 3. So I have 3 units of unsaturation. Now, what are the possibilities? I could have, I don't know, a triple bond and a double bond, a triple bond and a ring, 3 double bonds, a ring, 2 double, right? There's all kinds of different scenarios that I could have. But I know that I've got at least a double bond to oxygen. I know I at least have the carbonyl in there. All right. What else? Is there anything interesting that we can garner from the mass spec? Okay, nitrogen rule. We have no nitrogen present. Okay, we'll just cut it off short here. There's no N plus 2 ion, so no chlorine, no bromine present. We're given the molecular formula anyway. Something else that's interesting is that you see you have the molecular ion. There aren't a whole lot of fragments in here, but I have a fragment right at 56. Now 56 is half of my molecular ion, right? This is like 1/2 of the molecular ion. 112 multiplied by 1/2 gives you 56. So this suggests to me that there might be some symmetry in the molecule, right? If I have this giant, or this large peak at a mass overcharge of 56. All right, I've got my carbonyl. I've got no nitrogen, no chlorine, no bromine. I've got 3 units of unsaturation. And in my carbon spectrum, I only have 2 types of carbons. I have some methylenes, and since this signal doesn't show up in the depth, that tells me that this must be the carbonyl, okay, like that. So there's a carbonyl. Now, this is something that you can't hitch your wagon to every single time in organic chemistry. But another thing I notice here is that we don't use integration for carbon spectra. However, you see that the relative height of this signal versus this signal, this one's quite a bit bigger, right? Okay, that suggests to me that I have more of those carbons, which produce that stronger signal, if you will. And so I probably have more methylenes than I do carbons with carbonyls on them. Let's go down to our proton spectrum. I literally have 1 type of hydrogen in the molecule. They all must be equivalent because there's no splitting, okay? So the only thing I have in here are methylenes, and they all must be identical. So there must be symmetry in the molecule if there's no splitting in the proton NMR. Well, I'm just going to throw this out there to my students who are very good problem solvers. Does anybody have an idea? Okay, and again, I know that sometimes these molecules might be difficult to name, or a cyclohexane with 2 ketones opposite of each other. Hot diggity darn, Scott, that's a pretty good way to describe it, right? Another thing that some students like to do once in a while in my Gen Chem, when earlier this semester we were looking at Lewis structures, you'd have to be really quick on this, but I had 2 or 3 students who were taking pictures with their iPhones or their smartphones of their scratch paper, and then they'd post it to Microsoft Teams. I don't know how they did it so quickly, but you could try that too. But Skylar says this. He says, what if you had a cyclohexane, okay, like this. You had 2 ketones, and they're opposite of each other, okay? This is called 1,4-cyclohexane dione, but that's neither here nor there. That's another day. Well, you can see that we've got reflectional symmetry here, and we have reflectional symmetry here. Therefore, just with respect to our carbon-13, each one of these carbons that I'm highlighting in yellow is chemically equivalent. And also, our 2 carbonyl carbons are chemically equivalent. That explains why we have only 2 signals in our carbon-13 spectrum. Let's draw the compound, our cyclohexane with 2 ketones opposite one another. We should talk to IUPAC about changing the nomenclature rules. Anyhow, we have A right here, and then we have B. And if you have to draw a little arrow like that for your B carbons, I would say that is perfectly annotated. There's nothing wrong with that at all. If you really need to label all of them like this, you can do that. It's not a big deal, but your instructor, she or he will understand, which carbons and which protons are chemically equivalent and which ones aren't. Okay, next we have our proton, and I think you should be able to do that pretty quickly. So we'll draw our 1,4-cyclohexane dione. There we go. And like that. And we only have 1 type of hydrogen. We can draw the 2 hydrogens like this. I like to put a little subscript like that. Can get really handy when you're looking at proton spectra that are a little more complex. You could do it that way if you just want to make it really simple and just put the letter A next to the carbon that has the protons, and you say, well, all of them, they're all chemically equivalent, right, because of my axes of symmetry. That works for me too. Nothing wrong with that whatsoever. Okay, so what did we do here? We started with cyclopentane, not too bad, only 1 type of signal there. Then we spiced things up. We looked at a proton coupled carbon-13 NMR spectrum. Let me just put this bug in your ear. For my students who might be interested in writing a standardized exam in the future, I'll level with you, even though this doesn't come up in, or it's mentioned, but I don't think there's any examples in the lecture textbook, in the David Klein textbook. In the ACS study guide, there's always a few questions where they bring up the proton coupled carbon-13 spectra. So make sure that you're aware of this. If you're the kind of person who might want to write a PCAT exam or something of that ilk, an MCAT or a DAT, you might want to have that in your hat. Okay, there we go. So we went from butanone. So technically the name of this compound isn't 2-butanone, it's actually just called butanone, but that's neither here nor there because, well, anyhow, I won't explain why. Talk about that later. There we go. So, and then we did 1,4-cyclohexane-diene. All right, let's move along. Hey, I'm just going to throw this out there to my students who are very good problem solvers, which is all of you. Sorry, I'm having a problem with my MacBook. There we go. Hey, does anybody see any quote unquote low-hanging fruit in the IR? Just going to throw that out there. Is there anything in the IR that catches your fancy or gets you thinking right away? Anything that, you know, just your attention is drawn to immediately? It's not an alcohol. It's not a carboxylic acid. Somebody says 1,500. Okay, yeah, there might be something around 1,500. But what is it around the neighborhood of 1,500? What do you see there? What kind of functional group might we see there? All right, what are we seeing? What about students seem to be obsessed oftentimes, and I don't mean this in a bad way, with signals that come between 2000 and 1667. Does anybody remember what these are called? These signals that we have here, they have a sassy little name for them. The overtones. Yeah, overtones. No, okay. Well, overtones come from an aromatic ring, right? And here you can see that we have between 1600 and this is 12, 13, 14, maybe 1450. Usually when you have 2 to 3 signals in the 1450 to 1600 range, that tells you that it's a carbon-carbon double bond and that it's aromatic. Okay, so that means that we must have an aromatic ring in our molecule. We've got that. All right, we've got an aromatic ring in there. I don't have a ruler, but if we draw this here, you know, you could say we have some sp2 hybridized carbon-hydrogen bonds here, right, from our aromatic ring. So we have an aromatic ring in our molecule. Look at this. We've got an M plus that's 170 and 172. Ooh, baby. What do you notice about this molecular ion? That's the best I can zoom in, and I know it's really small, but can anybody draw a conclusion about the molecular ion in the M plus 2 peak here at 172? What's the relative height of these two peaks? What does it look like? Yeah, thanks, Stephanie. Absolutely. Stephanie's 100% correct. So what Stephanie said is that she said, well, look at the height of these peaks. They look to me like they're in about a 1-to-1 height ratio, right? So Advita says 2 equal peaks. Exactly, right? The relative abundance of bromine 79 and 81 is what? 51 and 49%. And so we get roughly a 1-to-1 peak height for the molecular ion and the M plus 2 peak. So that tells me that I have bromine in the molecule. And if you're like, Mr. Dion, I knew that from the formula. Well, you know what? Maybe I'll give you a question where I don't give you the formula. So you'll have to figure that out. Okay, so we know that we have an even mass. So we'll write no nitrogen present or an even number of nitrogens. We'll put here no Cl present, but we'll put bromine is present in our molecule. I want to test your memory, and there is a fragment that I talked about quite a bit with you. I feel like I yammered on a little bit about it when we did our lecture on infrared spectroscopy and mass spectrometry in this class. And again, if you're in the lecture course, I would have talked about this fragment too. Does anybody remember what a fragment at 91, what that represents? It's a very common, I shouldn't say common, no fragments are common unless it's in the molecule, but it comes up a lot in undergraduate chemistry, I would say. Anybody recognize that guy? Because if you knew the fragment, this would be a dead giveaway. So let's skip that. Yeah, Skylar says aromatic, question mark. You're in the right vein. You're definitely in the right vein, right? Because if you have a phenyl, right, if you have this ion, right, that's got a mass over charge of 77, and 91 is more than that. What did Advita put? C7H7. Yeah, you're definitely in the right vein. That's the right formula. Yes, it's C7H7 plus. That's a good answer, Advita. That's a very good answer. But there's a name for it, and you know what? Let's just skip it. Let's take a look at the carbon. Where am I? Okay, let's see what we have here for signals. Let's look at the proton decoupled, then we'll go over and we'll look at the depth spectrum after. So what we're looking at is all of this here, okay? This is my proton decoupled spectrum. Now you notice that these signals are pretty close together, and so what they've done is they've taken them here and they've expanded them so that we can clearly see how many signals are in the spectrum. So we've got A, we've got B, C, and D for those three carbons. We have E for this guy. So that means that in this signal, or what looks like one signal, it's not, but you have B, C, and D, and then this one is E, and that's it. Okay, those are all the signals in my carbon. Now, what's the identity of those signals? Well, A must be a methylene, okay, because it's pointing down. If you look at every other signal, because they're expanded up here in the depth, all of those signals are pointing up, okay? They're shifted too far downfield to be methyl groups, and therefore these must all be methylenes, okay? Or sorry, methynes. So that means that B is a methine, so I've got a methine here. I've got a methine here for B and C and D, okay? And then E is missing. Sorry, I missed E. I missed it because it's missing. E is missing, and E must be a carbon that has no hydrogens attached. So this is E, is carbon that has no hydrogens attached. All right, some other, finer points here on the carbon. And, this is something that I went over with you a little bit in class, is if you just look at the expansion quickly, and again, like the way I phrased it earlier today, I said you can't hitch your wagon to this 100% of the time, but you see how the relative peak height of B and E is smaller than that of D and C. D and C are a lot bigger, okay? So that suggests to me that D and C might represent more than one carbon, but we'll wait to see. The verdict's still out on that. Okay, we'll look at our proton NMR spectrum. I've got A and I've got B. What are the relative heights? If you measure the relative heights of these, and I've gone ahead and done that, and we know that there's a total of 7 hydrogens in the molecule, this signal represents 2 hydrogens, and this multiplet here represents 5 hydrogens, right? We say that this is a multiplet because there's no defined splitting here, not that we can tell. All right, so we have a singlet that integrates for 2 protons. We have a multiplet that integrates for 5 protons. These are in the aromatic region. So that tells me I must have a monosubstituted aromatic ring, right? My aromatic ring has something attached to it, and all 5 protons, okay, are in the B signal here. And then I know that I also have a methylene, okay? And what else do I have in my molecule? I also have a bromine in my molecule. That literally leaves me with only one way to put everything together. If I have this piece, and a bromine. The only way that I can put those together that makes any sense would be to have my aromatic ring, like this, okay? My CH2 group, my methylene, and my bromine, like this. The name of this compound is benzyl bromide, okay? It's really good if you want to do an SN2 reaction or an alkylation. You need to add a benzyl group. Also, benzyl bromide is a very strong lacrimator, horrible lacrimator. In fact, benzyl chloride is also a lacrimator. Does anybody know what a lacrimator is? This is benzyl chloride versus benzyl bromide. No, nobody knows what a lacrimator is. Anyhow, if you've ever chopped onions, and the sensation that you get where it makes your eyes water, Well, if you're ever exposed to benzyl chloride, take that and multiply it by about 10. Yeah, exactly, Jonathan. An eye irritant. So benzyl chloride is like 10 times worse than an onion, and benzyl bromide is like 10 to the power of 10 times worse. It's not, maybe not that much. The benzyl bromide, if you put one drop on the floor, everybody will know. Trust me. It's happened to me. Right? Okay, anyhow, benzyl bromide, very powerful lacrimator. Where was I? Let's get back into annotating our spectrum. We have the A protons, so that's the methylene protons. For my B protons, since they're not all chemically equivalent, I'll put B like this for all of them, and that encompasses all of the 5 protons in the aromatic region. For my carbon, I don't have a lot of space here. I'll draw the molecule up here. And please, for the love of Pete, draw the molecule twice. Okay, don't be so slothful that you only draw the molecule once and then you try to annotate it for the carbon and the proton. Just draw it a second time, right? So A must be my methylene because it's pointing down. E, this guy here, is the only one that disappeared in the depth. Therefore, it must be this guy. If you look at D, C, and B, since B is further upfield and it is a smaller height, I'm going to say it's this one here because that one is chemically unique. Then I have D and C. Since D is a little more de-shielded than C, I'm going to say it's the one that's closer to this spinach over here. So I'll put my D like this and C. And if you're unsure, if you put D and C like this, it's okay. Okay. It's not the end of the world. Then if you're like, well, can't I just do that for everything? Just write A, B, C, D, E by every carbon and ace the assignment. No. But if it's really difficult to tell and you assign, 2 carbons the same letter, it's not the end of the world. Okay. It's not the end of the world. So you could do it like that. That's totally fine. Or if you just want to be unequivocal about it like this, that's fine too. All right. Let's move on from there. So benzyl bromide is a compound that shows up a little bit in organic chemistry too when we look at peptide synthesis and some other reactions along the way. Here we go. Well, let's look at problem number 5. I'll give you a second to look at it. Problem number 5. All right. Well, I'm just going to throw this out there to my students. If I kind of help you out here, and of course, when you're doing your assignment, you're going to have your IR and NMR tables to aid you. There's nothing wrong with that. I call those training wheels. It's nice to, everybody looks at those tables once in a while. Everybody does. But the more signals that you have committed to memory, the more, I'd say, the more rewarding solving spectroscopy problems gets, the quicker it goes. If I circle these 2 signals, I have one at 1725, the other one's right around 1200. Could anybody tell me what functional group is highly probable here? I looked up, Jonathan, and I saw eye irritant. That's not a functional group. No, can anybody tell me what this might be? Notice that this absorbance is really strong. Okay. Well, if you look at the David Klein chart, and I have it here, I can't see it, but if you look at what it says for an ester, it says 1735, you have carbonyl stretching, but then between 1300 and 1000 reciprocal centimeters, you have a carbon-oxygen stretch. Whenever you have a stretch here, the carbon-oxygen stretch being a very strong absorbance, this a lot of the time is a giveaway that you've got an ester. Yeah, you've got a carbonyl here, and you've got a carbon-oxygen single bond here that probably are a result of an ester being in your compound. So we'll put here an ester present like that. I don't see much else in the IR spectrum right now. It's not an alcohol. It's not a carboxylic acid. It's not a primary amine. It's not a secondary amine. It's not an aldehyde. If you draw a line here at 3000, you draw a line right at 3000. Come on, you. Like that. Will this work? Yeah, like that. So if you draw a line at 3000, we don't see the aldehydic CH stretching, right? Aldehydic CH stretching, this CH stretch, this is at 2850 and 2750 reciprocal centimeters. We don't see that. Okay, so we might have an ester in our compound. Let's take a look at our mass spec. Seems like I'm always waiting to get down to the molecular formula when maybe I should look at that first, but whatever. Let's see here. We got a molecular ion that is 74. Okay, so we can say there's no nitrogen present or an even number of nitrogens. We don't have an N+2 peak. Right, there might be a fragment there, but it's definitely not a chlorine or a bromine. And so we'll say no chlorine or bromine present in our molecule. I see some fragments here. I see a fragment at 45. I see another fragment at 31, another one at 29. Does anybody remember the fragment at 29? This is a fragment that came up quite a bit in class. Does anybody remember what a fragment at 29 might be? Remember, we looked at masses like 15 and 29 and 43. Oh, what did you put, Lillian? Cha, perfect. Yes, 29 is probably an ethyl, right? An ethyl cation. Yes, yes. So we might have an ethyl group in here. You know, and if you wanted to answer that question, what could you do? You know, maybe scooch down to the NMR right away and see you've got what looks like a triplet here that integrates for 3 protons, and then you've got a quartet here that integrates for 2 protons. So yeah, it seems to me like we might be onto something here, that we've got a ethyl group in our molecule. Anyhow, let's go back to our molecular formula, C3H6O2. We calculate the HDI. It's equal to 1. So that means if we have an ester in our molecule, if we have this in our molecule, and we have an ethyl group, CH3, CH2, right? We have an ethyl group somewhere in our molecule. Another, other ones that would be handy would be 45. If you take 29, where's my calculator? If you take 29 and you add 16, what do you get? You get 45, right? So that makes me think, if you have 29 for the ethyl, what if you have an ethoxy, right? If you had this cation, that would have a mass over charge of 45. So we might have an ethoxy. Anyhow, that's enough of that. Let's move on to the carbon. Let's annotate the peaks first. So we have A, B, C. We've only got 3 carbons. This one must be a methyl group. This one here is a methylene group. And this one here must be my carbonyl, right? Because I know I have a carbonyl for sure in my molecule. That's probably an ester. So what have I got? I've got a carbonyl, I've got a methylene, and a methyl. Makes sense because I think that there's a methyl in the compound, and I think I have an ester in the compound. Before we move on, I'm going to move some of this junk out of the way, and I just want to take a long, hard look at what we've got. Okay? This is what we've got so far. We've got an ester. Okay? We've got an ethoxy group. That's what we've got so far. Well, there's only 2 oxygens in the molecule. So that means that this ethoxy group must be attached here on my ester. Okay? This isn't the best way of doing it, but there you go. Like, we must have that in our molecule. If you calculate the molecular formula of what I've got drawn right here, okay, if you calculate the molecular formula of this, I've got C123, H12345, O2. Okay, where's the other hydrogen going to go? It's going to go right here. And then you're thinking, Mr. Dion, that's an aldehyde. No, it's not. That's not an aldehyde. Okay, that's an ester. Okay, if you have a hydrogen attached to a carbonyl and then you have an R group, that's an aldehyde. If you have an oxygen, then an R group, that's still an ester. It's called a formate ester. Okay, but it's still an ester. So I'm going to propose this before we even look at the proton. Now let's go ahead and take a look at our proton NMR spectrum. Okay, so we've got 3 signals, A, B, and C. I've gone ahead and measured the integration, the step curves already, this one here, this one here, this one here. I've got a total of 6 protons in my molecule. This signal integrates for 3 protons. This signal integrates for 2 protons, and this signal integrates for 1 proton, like that. You can see that this signal here looks like a quartet. So this is a quartet. This signal here is a triplet, which makes sense because we think we have an ethyl group in our molecule. And then we have the other proton that isn't coupled to anything. It's not split in any way. Does all of this make sense? Heck yeah. If I draw the structure of my proposed ester, okay, I have my C proton, the one that's attached to the carbonyl, which is going to be the most deshielded. So we'll call that HC. I have the methylene protons, which produce a quartet because they're coupled next to the, sorry, I'm having a problem with my MacBook. Yeah. Coupled next to the 3 protons of the triplet, so it produces a quartet. So we have B and A, and there is my proton NMR spectrum that is annotated. Let's go up to our carbon. I'm going to redraw the molecule. I'm not going to try to plaster my carbons assignments on the same molecule. So I've got 3 carbons. I know that this one, the carbonyl, must be C. My methylene is B. And my methyl group is A. All right. So the name of this compound is, this is called ethyl formate. Or you could call it ethyl methanoate, but you'd have to be in a asylum or something to call it that. Well, let's take a look at question 7. You know I have a few students who are online right now who are doing biology degrees and are probably familiar with the Krebs cycle, right? The citric acid cycle or the tricarboxylic acid cycle, whatever you call it. Anyhow, and I bet you know all kinds of intermediates, like, I don't know, what's an intermediate in there off the top of my head? I don't know. What would be citrate, isocitrate, oxalate, right? Succinate, all those good things, right? So it's a good idea to memorize the dicarboxylic acids especially for my students who are in biology. It'll really help you out, when you're looking at intermediates in the Krebs cycle and you're trying to memorize the intermediates. Now, the acronym that I remember, actually I don't remember it, is what? Oxaloacetate is Krebs special substrate for, no. That's what it is. It's pyruvate. So you should know what pyruvic acid is, right? Pyruvate, gets activated by acetyl coenzyme A. Anyhow, so you got pyruvate is Krebs special substrate for making oxaloacetate. Anyhow, I don't know why I'm talking. I do know why I'm talking about the Krebs cycle, because what I'm trying to get across to my students is if you can memorize the structure of a few dicarboxylic acids that you learn in organic chemistry, you'll learn them in organic chemistry too, but those acids will really help you when you're studying the Krebs cycle and you want to write out the structure of an intermediate, right? A lot of the students who are taking this class are going to take biochemistry, and so those are things that are really handy to know, right? Because you're going to look at, study, the structures of like nicotinamide, adenine dinucleotide, and all that kind of good stuff that I've forgotten. But anyhow, so I want you to have that in your brain while we take a look at this problem. So let me just walk you through this one. I've asked you guys quite a few questions. What time is it? It's 1:30. 1:15? 1:13. Okay, we got time. Look, we got a strong signal here at 1739. I also noticed that there's a really strong absorbance here too. Now, you might be thinking, well, it's kind of in all this spinach, Mr. Dion. Well, remember that when you're analyzing infrared spectra, you've got to be able to separate the noise from the signals, right? Now, so what that means is you've got to be able to pick out what's most important in there. Again, as I mentioned earlier today, if you have an ester, the carbonyl stretch is usually going to be in that 1725, 1735 neighborhood. And we also have a really strong carbon-oxygen absorbance down here below 1200. It's around what, 1175 maybe? So right away, I'm thinking, carbonyl and probably a carbon-oxygen single bond. And I'm thinking that this is probably also an ester, that we have an extra functional group. Look, we don't have a carboxylic acid. We don't have an alcohol. We don't have an amine. We don't have an aromatic, right? We don't have an aldehyde. Yeah, so that leaves us with an ester is what it looks like to me. Now, let's take a look at the mass spec. Now, as I told you, sometimes in a mass spectrum, we don't even get the molecular ion. You don't even see the molecular ion in this spectrum, or maybe it's there. Yeesh, if it's there, it's tiny. Okay, it says it's less than 1%, your molecular ion. I think it's actually this nub right here. That's your molecular ion, which has a molar mass of 116. So let's write down no nitrogen present. What else? We don't have an N+2 peak. So we have no chlorine, no bromine. We have our molecular formula. Let's go ahead and calculate the HDI. We've got an HDI that is equal to 2. So we've got 2 units of unsaturation. At least one of them is a carbonyl. The fragments, we got a fragment at 59. We've got a fragment at 87. But anyhow, the fragment at 59, I don't think I ever went over a 59 fragment. If you look in our lab textbook, I bet you could find a fragment for 59, but let's move on from there. Let's take a look at our carbon. Let's see, we've got A, B, and C. A is a methyl group, must be because it's so far upfield. We've got a methylene here, and we've got a quaternary carbon here, or a carbon that has no hydrogens attached to it. So this must be our carbonyl. It's above 150, so that makes sense. So we've got a methyl, a methylene, and a carbonyl. So that's 3 carbons accounted for, but when you look at your molecular formula, there's C6. So this suggests to me that there might be some symmetry, right? There might be some symmetry in this molecule. If I only see 3 carbon signals and I've got a total of 6 carbons. Let's go down to the proton NMR spectrum. I've got 2 singlets. That's it. This is a singlet and this is a singlet. Now, I went ahead and measured the height of the step curves, and the relative height of these step curves is 2 to 3. So it's a 2 to 3. No, what did I get? Yeah, 2 to 3 ratio. But if you look at the molecular formula, you have a total of 10 protons. Now, 2 plus 3 gives you 5. Did I measure those correctly? No, that's not right. This height is bigger than this one. Nobody stopped me. So this one has a relative height of 3. There we go. And that one has a relative height of 2. That makes a lot more sense, doesn't it? Okay, where was I? So I have 3 and 2, but again, and we're running out of time. So since there's a total of 10 protons, this one must represent a total of 6 protons, and this signal must represent a total of 4 protons. There's no such thing as a carbon with 6 protons, so this tells me there must be some symmetry in the molecule. All right, so I've got an ester. All right, what have I got? I've got an ester of some sort. I've got a methyl group, and I've got a methylene group. All right, now, if I tally up the molar mass of all that, if I take 15 plus 14 plus 32 plus 12, I get 73 times 2, which gives me 146. So if I tally up the masses of all the fragments that I just wrote down that I know, if I multiply all this by 2, I get 146. So that tells me that these are the pieces that I need to put my molecule together. There's really only 2 possibilities here. Okay, there's only 2 possibilities. Let me show you what they are. If I have my 2 methylenes like this, and I have my 2 oxygens like this, and my 2 carbonyls like this, this is a possible structure, isn't it? Now, this, I'm not saying it's right, but it's a possibility. right? This methylene and this methylene are chemically equivalent. They're not going to split each other. So I'd get a signal for 4 protons here because of the axis of rotational symmetry. These 2 methyl groups are also chemically equivalent. But if you look at the integration in the proton NMR spectra, you can see that the methyl groups are shifted further downfield than the methylenes. So does this structure make sense to you? The answer should be no, that this structure doesn't make sense. Because remember that if you do the baseline calculation for a methyl group, we have 0.9 parts per million plus 1 from our carbonyl, which would give us a chemical shift for our methyl group of around 2. But you see that it's up around past 3.5. So if I fix this, let's say I put the ester oxygen on the other side of the carbonyl. And if you're like, what do you mean by that? Watch. If I erase all this spinach here, and I do something that looks like this, where I have the carbonyls like this, and then I have the methyls attached to these oxygens. That makes a lot more sense, doesn't it? Right, because now this methyl is going to be shifted further downfield than this methylene. The methylene should only have a shift of around 2. It's a little bit higher. And the methyl should have a shift of around 0.9 plus 3, right? So that gives me around 4. That makes a lot more sense. So this is the molecule that I'm looking for. So the name of this molecule is dimethylsuccinate. So if you were to, change both of these to hydrogens, right? If these were both hydrogens, that's succinic acid. It's a dicarboxylic acid, which again, if you're doing a biology degree, it's handy to know the structures of dicarboxylic acids. So we have dimethylsuccinate. Let's annotate our carbon spectrum. We have our A carbons. We have our Bs, which is our methylenes, and we have C for our carbonyls. Let's do the same thing for our proton NMR spectrum. Redraw the compound. Ink is cheap. Paper is cheap. Like this. We have 2 kinds of protons. We'll call these the A protons and the B protons. Again, we're annotating going from right to left. It has to be done in that manner or it's not correct. Okay, you cannot receive full points unless the spectrum is annotated properly. We have A for our methylene protons, and we have B for our methyl protons, like that. And there you have it, dimethylsuccinate.